I would like to make a comparative distinction between deep neural networks that many of you know and physical neural network. So deep neural networks have become a pervasive tool in science and engineering and is on the way to becoming a very, very pervasive tool. Hopefully, we will not forget about physics in that process. But what it is, at least what it is, what it boils down to is a set of well-defined mathematical transformations, programmable mathematical transformations that take an input u, let's say a vector of inputs, and define a function of that u in a programmable way. Yeah, and it's good to think of this in two steps, and these two steps are not necessary, but it helps us in explaining certain things. One should think of this mathematical transformation as a well-defined mathematical transformation that you apply on a digital computer with a certain parameters, additional parameters theta. And at the end, when I look at the nodes, I get a set of features, x of u, it's again a vector. And then I will imagine that I will find the appropriate real numbers w that multiply these features so that we can represent this function f. And so we'll be focusing on the inference phase, which means we assume that the other internal parameters theta here are fixed, and and what are those functions we can build out of this by playing with this w. Now, a physical neural network, on the other hand, is a transformation by a physical system of an input stimulus, maybe electromagnetic waves, and a measurement of this transformation, which generates a set of measured features that I will denote by capital X, which then, of course, will depend on my input, u. In this case, I look at a very particular thing so that it lightens up something in your mind. The optical system is very nice because it's visual. So in that case, the input u would be the pixel values on a spatial light modulator that acts on a Gaussian beam of light that gets transformed by a complex physical system. I just put this thing, but imagine it's a complex physical scatterer. And then I make measurements. So and then I want to find these w's and see, with playing with w's, which functions I can generate of my input. Yeah, and so it depends on initial condition of this system, x of u, of course. And so the question is, how is this different from that? Well, in several ways. Here, we typically imagine the inputs u to be stored in memory in a digital system somewhere. It's pulled from the memory, put into an algorithm that runs on a digital computer, and it goes through a process, spits out the answer for the features, and then I do this, right? Here, the input is a physical input. It's light, electromagnetic wave, a stimulus. The measurement, right, is a physical measurement. There's a transduction along the way where light is turned into electronic excitations, which we read out, right, in a photodetector array. And those results are stochastic, right? And we typically come up with a way to bring down that stochasticity, like an integration time, right, at delta t. And so our features, which are sort of the number of clicks in each of these detectors, are stochastic variables. Okay, so that's really the key difference. So input is physical, transduction is physical, measurement is physical, and they are limited by physical laws of nature. Okay, so now we can study this as physicists and understand the fundamental limits. Yes? Yeah, so, you know, in general, we think of this system being, for instance, a set of microwave oscillators, superconducting oscillators, it could be. Then I would have to start. Before I start putting the stimulus in, it starts in an initial state. And maybe that initial state is a thermal initial state, right? That's why here it doesn't make much sense. You're right. So I hope this sort of, you know, starting point is clear. Yeah? Now, I will claim that many physical systems potentially used for computing have the same nature. The brain, in many respects, is very similar. There, let's say in this example, the input U is an optical stimulus, right? A scene that is emerging on the eye, and then that goes electrically sort of transduced to electrical activity in the neurons, and then nowadays we have these incredible sort of imaging techniques based on calcium imaging that I can record the activity in individual neurons with very high spatial resolution, and I can detect those neurons, and you see these are in this case my optical stochastic features, and they are stochastic. What that means is even if I give the same stimulus to this mouse, let's say, and I keep the environmental conditions the same. The mouse is equally hungry, the mouse is equal temperature and so on. When I give the input stimulus again, you will receive a sequence in the same neurons that is very different than the previous sequence. Yeah? So the encoding is very stochastic, okay? So how, a key question in neuroscience, as I understand from my colleagues, is that despite the stochasticity, how is animal behavior so robust? Yeah, it's a very interesting question. But to me, as a physicist, this actually system is really no different from a quantum computer, because when I take a standard circuit gate-based quantum computer, measure, put an input in through some unitary that we'll discuss, make measurements at the output, look at the occurrence of binary strings for S shots. It's a typical experiment you do in quantum computing. You will find that if you repeat this S shot, this histogram will be slightly different, okay? And it will fluctuate quite a bit. And so to me, the systems are identical. And I will try to, and I'll try to make the point that there is a unified description of all these physical systems. Okay, and let me come to the fundamental limits question. These fundamental limits should not be thrown around very broadly, but I feel should be defined very concretely. So I want to sort of frame what I mean by fundamental limits in terms of a Gedanken experiment. Yeah. So this is, as some of you know, who has taken electrical engineering course, this is a typical MOSFET circuit that implements a NAND gate. It's old technology now, but the principles are the same. So, and what we have here is an input-output system where the inputs take logical bits 0 and 1 encoded in terms of voltage levels, either, let's say, 1 point something volts or 0 volts representing bit 0. And the output is, again, a bit-valued function. It can be 0 and 1 or 0 and 5, plus V volts. And this, by design, represents, approximates this function, bit-valued function. Okay, it's a function. And now the question I want to answer, or ask first, we didn't answer yet, but I think everyone is free to think about this. If I reduce the voltage level of the logical 1 encoding and make the energy in the pulse smaller and smaller gradually, can I still be very accurate, remain accurate in representing this function? Yeah? And of course, the usual refrain is that once the level comes below the sort of Johnson-Nyquist thermal fluctuations in voltage, I should not be able to distinguish 0 and 1, so I should be making a lot of errors. Now I want to claim that that if you now take a different perspective and think of this as a dynamical system that tries to approximate this function on this stimulus, that you can show that input power, when input power is decreased, maintaining computational accuracy for this function, let's say, requires increasing the nonlinearity of the individual elements here with a certain power law depending on the power in the pulses. So that's actually something we have studied not with MOSFETs, but with a generic nonlinear oscillator with a quantum description of it. And you can, and the only difference, I guess, to this scenario is that there's a carrier wave on which these pulses are included, and the frequency of that carrier wave is resonant with the individual oscillators, so that you get a large nonlinearity, resonant nonlinearity. So that little result is in this very old unpublished work. Okay, so now I want to try to make the point that when you do this Gedanken experiment and you increase the nonlinearity to sort of maintain the accuracy the same, you actually reach the quantum computing limit, the limit at which we operate quantum computers. So here I have an example, let's say, symbolic example of a 4-qubit circuit. And these qubits in microwave domain, the reason they work is because they are extremely nonlinear with respect to the dissipation in the system. And so that's the extreme nonlinear limit. And the input pulses that I sent in order to encode a certain input are actually gates. And gates are single photon pulses in a way. Yeah? So I've reduced really, in principle, though it's not true in practice, the pulses that I sent into a quantum computer, superconducting quantum computer, are 1 photon level pulses. Yeah. And so now I want to discuss sort of, with this understanding that quantum computing is very, I think, powerful to think of quantum computing as a physical computer operating in the low power limit, is what I'm trying to say. And it will bring us to some certain conclusions which are very useful. So here now I'm thinking of a circuit-based quantum computer, and I want to illustrate what we mean by a physical neural network in terms of how you would implement it in practice with a quantum, gate-based quantum computer. With a toy problem, which is very easy to understand. The toy problem is the following. I have a two-dimensional domain of values u, which is compact, and it's coming from 2 probability distributions, P1 and P2, different colors, right? They have this structure of a spiral, right, each point. And this is called the spiral classification task that some people use because it's nonlinear, not a linearly separable sort of binary classification task. And I want to put this in U, and the way we do it is through parametric circuit learning, is we encode the Hamiltonian with parameters that depend on that input U. So I draw a u1, u2, a point here. With those two numbers, I come up with the Hamiltonian, and then I evolve it for a certain time. That it's the input encoding. And then I make measurements, right? And the measurements for one shot is sort of a bit string that I will get out of this result, right? And so ultimately, I'll get measured features X. And in this case, the measured features have typically, in literature, it varies. You can take expectation value of individual Z, sigma Z expectation values of individual qubits and make them a vector, right? And this vector depends on U now, because you have done it for a particular U. And now my X of U, I'll try to find the W by data-driven training that gives me the function U that I desire. And what is that function U? Well, it should be 0, let's say in one way of doing it, when the data U comes from S1, and 1 if it comes from S2 distribution, from the probability distribution 2. Yeah? So it's really a function, and so it's good to be able to touch classical domain and think of functions. And then I want to define this particular quantity we call capacity, but it's nothing but 1 minus the mean square error of that function fu with the target function f star, right? And when these quantities are properly normalized, there should be also a pu, okay, which comes from there. When these are properly normalized, then this number c, the capacity for this physical system to approximate this target function f star, is a number between 0 and 1. Okay? So if it's 1, it means I can find a W that gives me exactly my function f star. And if it's 0, if that function f is in a certain orthogonal space to f star, yeah, where the weight function is given by the probability distribution pu. Okay, so just to sort of drive this home, I'm plotting now, after I trained W, a set of real numbers as big as this, by showing some data, which are there. This is training data. I plot this function by just scanning U1 and U2, and you see it's a function like that. It's a false color plot. And in these dashed line, I show the classification boundaries, which is a ground truth. Yeah. And you see it's close. It doesn't matter, but you see, I want you to visualize this function. And so these are the test points and samples that are correctly and incorrectly classified. These guys are incorrectly classified, for instance, and you get 94% capacity. Yeah? Now, how do we think of the space of functions that this physical system can create by just playing with this W on the measured results? Yeah? What is the space of functions? So there's a very neat way of measuring that. It's called total capacity. And what you do is you come up with a set of orthogonal functions FL, infinite in number, that lives in your input domain. And you find the capacity for each of them. You sum this infinite sum. And the very interesting result is if these functions are normalized properly, then this total capacity is as an upper bound given by L, where L is the number of independent measured features. And this, in practical cases, is an equality. Yeah, not this, but an equality, unless you choose an encoding that has some symmetry in it. Yeah. So this is a result from this paper, which we found very inspiring. And so I just want to show you how, this idea works in practice. just through numerics. This is for a physical system of 6 qubits, in certain parametric encoding of the input. And the input is one-dimensional and compact between -1 and 1. And so you know that a nice set of orthogonal functions that live in this compact domain is Legendre functions, right? And I'm showing the first many Legendre functions. There's a break here, right? That's 49, 50. And I show you the fits, and the fits are pretty close for low orders, but it gets worse for higher orders. Now the magic is if I sum this up to infinity, it's going to be the number of independent variables of that physical system that tries to approximate this function. Okay. Now it's interesting that this limit, the total capacity limit, is actually turns out to be the same for any physical system. Yeah, any physical system with the same number of independent measured features have the same capacity, which is not our experience. Yeah, I mean, anyone experimentally who tries to do this will find that this is a joke, right? And I will come. And I will say part of, I want to say that really the sort of the thing that makes actual physical systems interesting is noise. Yeah? And so if you actually include sampling noise, shot noise in this quantum physical system that does the processing, then you find that the capacity are very different, and the best fits are showing in these things, and these are like stochastic, as you see, functions, yeah? Okay? Which means if I do another experiment to do the same stuff, the function that I fit will be slightly different, yeah? But it will fluctuate around that much. Okay, question?
In the projection you showed on the slide before, you used a linear projection.
Yes, yes.
And then you look for like the W's which fit the best.
Yes.
Would allow for a nonlinear transformation. Can you get better than this limit you have derived? Or?
Absolutely. I mean, I think if someone gives you a physical system, I can put a extremely deep neural network underneath it that will fit everything plus the noise. Yeah. Okay. But the key is that in this mathematical description that has, some of you may recognize the similarity to reservoir computing type machine learning, is actually the mathematical structure it gives. The reason we use linear projector at the end is because we want to measure the processing capacity of just my physical system, not some extra GPUs on top of it. And second, the fact that I have this linear projector in the output allows us to define a Hilbert space of functions, and that will make all the results possible that I will share now. Yeah.
In the experiments, you have the noise feature. I mean, I understand that the width of this represents the noise, but then why is it coming much smaller when you go to the projection of K, which is large?
Oh, here?
Yes, the noise seems to be much less than if you have K equal 1, for instance.
Good observation. I can't tell you right off the top of my head. This is actually a simulation that I asked my student to send me yesterday night from China. And the reason was to illustrate, so that we are concrete in what we mean by functions and so on. Yeah, but I will come to more rigorous examples and actually experiments, more importantly. So now the key is the following: sampling noise. So what do I mean by this? And I would like to be, any experimentalist knows what I'm going to tell you, but many theorists, including me, I didn't know. Okay. So let's say I have a simple circuit like this, and I have a two-dimensional domain of inputs U1, U2, And I take some points, U1, U2, U3, and I put it into the system. And the way I put it into the system is I parameterize, I use them as angles in this one-dimensional, in these single qubit gates Rx, right? So U1 has two numbers in it, so I parameterized these two angles. Then I make a measurement. And I repeat that measurement with the same U, and measure, let's say my features that I will use will be expectation value of sigma z1 and sigma z2. I will get this point for U1. For U2, I will get that point and so on, yeah? So, but the point is that even though as theorists we solve the Schrödinger equation and find this expectation value, in experiments, these expectation values are obtained from an infinite shot measurement. Infinite. You only can reach it with finite. With finite shots, you will reach some asymptotic limit, and you try to do your best. So here I'm showing when the expectation values that are computed again in this two-dimensional domain for these 4 points for different number of shots. And as you will see, and so this point is, let's say, I do 100 shots, I calculate the expectation value for this U, and if I repeat that experiment, I will get that, right? For these expectation values. And as number of shots increases, my distribution will narrow down. But what I want, and this is actually experiments of the same circuit, you can do it just writing a Python code in IBM. And you see these devices are pretty good, right? They produce the distributions that I get numerically. Now, the point I want to make is that this noise, you see, has a structure. Certain inputs lead to noises which are very narrow. Certain lead to very, Gaussian-looking things. And, one thing that I can tell is, for instance, this very narrow distribution is a situation where one of the inputs U has produced a Bell state. Yeah? Okay. So, and that's what sort of got us very interested, because this, noise in the noise in this thing is actually fundamentally dictated by quantum mechanics. And so if you try to build now a function by finding this W1, W2, for each shot, right, you will get a slightly fluctuation. And so these functions F are actually fuzzy functions, yeah? And so for every S-shot experiment, that function will be slightly different. And that's why the previous plot, is a particular S-shot experiment. Yes?
Start doing these real experiments, then you will have all kind of noise, right, entering. So it will not be just shot noise, but also noise.
Yes. So here I'll show you that in experimental systems they are shot noise limited. Okay. That's what we learned. At the moment. So I need to speed up, I think. So I want to now introduce this framework for quantum machine learning we call NISQ-RC, NISQ reservoir computing, that there's this question of what features should I use? And many papers in earlier literature use expectation values of certain observables. It turns out there's one set of observables that are functionally complete. And that's a set of observables that are formed, these features vector X, from histograms, okay, from the histogram, S-shot histogram of a particular experiment U. So now I will choose these sort of feature vectors for a given U as basically probabilities of that bit string, and so on. Yeah. So it's each entry is a value between 0 and 1. And then I will try to find this W to find this function FU. And you should prove that, and this is not, I believe is non-trivial, that this generates to the power L independent functions. So the number of functions in principle scales exponentially with the number of qubits L. And that's the same as the histogram having 2 to the power L features. No difference, right? Now, I'd like you to think now in this very high dimensional space of x1, x2, x3 individual members of this X for a given U. In this very high dimension, 2 to the power L dimensional space, I'll get a point. Yeah? But this point will fluctuate around depending on one experiment, next experiment, and so on. Okay. Now here's a one-slide summary of the mathematical result that we find very useful. So it turns out that this total capacity, you can do it for any physical system, including a quantum circuit like that, turns out to have this form, which is a sum over 2 to the power L numbers in the circuit L qubit case. These 2 to the power L numbers have this form, 1 over 1 plus beta k squared over S. Number of shots enters in this parametric fashion, and beta k squared are in a set of 2 to the power L parameters that characterize your quantum system and the encoding and so on. And these beta k squares are obtained by solving a generalized eigenvalue problem, and that's why this linear structure of the output space is very useful. All the nonlinearity is generated just by the physical system evolving. Yeah? And so these numbers, beta k square, will turn out to be very interesting and important. They tell me actually about the signal-to-noise ratio, inverse signal-to-noise ratio of the functions I can approximate. Yeah? But the eigenvectors corresponding to each of these beta k squares, which we call eigentasks, are more important. They tell me about special set of functions that I can build by choosing W's that, not W's, sorry, by choosing this vectors for W's that give me the highest signal-to-noise ratio functions which are ordered according to this beta k square orders. Yeah? And this eigenvalue problem can be constructed by experimentally accessible quantities. I will not get into this detail, but they have this structure. Yeah? Instead of dwelling on mathematical detail, I want to illustrate this thing in action. So this is a quantum circuit where we parameterize a one-dimensional input, right? And this one-dimensional input is really a toy input. No one does machine learning with one-dimensional inputs, okay? And we have do this on a 6-qubit computer, which has 64 features. And the way we parameterize the input, when we choose a U, pick a U, which we assume to be uniformly distributed PU, yeah? So any U value is equally probable. That U I put here in this RZ gate, yeah? And there's, so this is a particular U, and I will explain the reason why we chose this particular encoding. Some of you may notice that this is a trotterized form of a Ising model in a transverse field, where the Ising model parameters are characterized by this J. Yeah, okay. So then, before that, I'm showing one of the measured features here, xk. This is basically, the blue line shows the probability of getting a bit string 0000000. And you see it varies as a function of U. The blue curve is, I think, 16,000 shots approximately. And the other lines show numerical simulation with noise model of the device and without the noise model of the device. These features are pretty exact. Yeah, so it's, I will now, we will discuss how noise, as quantum computing experts would characterize, enters later. And here are the eigentasks. These are special functions that I can reach by linearly combining the features obtained from measurements with a certain set that is specific to this device. And I'm showing there are 64 eigentasks, and I'm showing every fourth of them. and I'm showing it for two values of shots, 16,000 and 1,000. The dark blue are 16,000, which has very little noise in it. And you see that if I now use the same parameters for this, the way I combine this, and I repeat the experiment for 1,000 shots, I'll get more fluctuations around this. And I can tell you that the capacity, C, as we defined 1 minus the loss of this function, fourth function, is really beta 4 square over S. The error is beta, expectation value of the error is beta 4 square over S, and so on. And as you see, they are ordered so that the noise increases in a fashion that is we expect. Now, I should speed up here. From a mathematical perspective, the distributions of beta k square, I'm plotting it, there are 64 beta k square. I plot these eigenvalues for two different circuits, blue and the other color, green? Red? Yes. We'll come to what it is. Consider for now the blue. And they have all this universal structure. So there's an interesting mathematical structure to this progression. This is semi-log plot, right? And so you see that if I now use, there's a simple sort of back of the envelope calculation for finding the total capacity. As you see, the eigenvalues that are less than beta k square less than S, they contribute a 1. Those that are larger than S, it's very small, so very large, so you will get 0 here. So you can say, you can draw an S, right, here, to the power 13 shots, and you look count the number of beta k squares, and that gives you the capacity for that S. And so I'm plotting that now as a function of S. I plot the total capacity for this blue curve again, and you see as a function of shots, this total capacity increases. So it's sort of, this means I can build 40 functions reliably at this number of shots. But you see the total capacity in the S equals infinite limit is 64. Nowhere close, yeah? And the numerical simulation for the ideal numerical solution is shown here. So you see this gap shows that we are shot noise limited, not error limited. Yeah. Okay. Now let's come to what these blue and green lines are. So red lines are, and so this blue line you see has a larger total capacity at a given number of shots. And this blue line is obtained by choosing a non-zero J, non-zero 2-qubit gates, whereas the green line is obtained by just using single qubit gates, J equals 0. So J is now an interesting hyperparameter that one would like to investigate. And if you plot as a function of J the total capacity of the system, then you will find that it flows this very non-monotonic curve, and that there is a maximum of this C at a given value of J. So the question is, what is that J, right? And that J turns out to be the J that is at the same level as the magnetic field you apply, and this is a random spin Ising model, so your system is sort of very responsive to how you encode your data. And if it was a clean Ising model, this would be the critical point of that Ising model encoding. So for good measure, we also plot that sort of a measure of correlations as a function of the same J, which follows the same pattern. So you see here that it's good to have an entanglement in the system, though it's just anecdotal evidence only. So I want you, this is a very crowded thing, I want you only to focus here. This is numerics, not experiment. And I'm showing here how total capacity increases for product state encoding. So the encoding U only is done via single qubit gates, and the entangled encoding, yeah, with a certain J. And you will see that they all converge to almost to the same thing, though the product state encoding sort of levels off very quickly. We don't understand the functional behavior here. But the main story here is that what entanglement seems to give you is a larger capacity for finite number of shots. Yeah. And so you may then wonder, how do eigentasks look for entanglement encoding and product encoding? And you will find that these functions are not very different, I mean, in nature, right? They oscillate similarly and so on. It's not that one is much more complex than the other. But what you can say for sure is that the product state encoding gives you a transition to noisy eigentask features much faster, right? There are very few high signal to noise ratio functions. So apparently entanglement gives you some protection towards sampling noise. And the way this happens, if you translate what we see into some sort of intuitive understanding, is that these features that you obtain have the noise is correlated between them. Yeah. So if one feature goes up, the other feature goes down, etc. So what's happening is by linearly combining them with certain coefficients, I can actually destructively interfere that noise and minimize that noise gets quantum erased, and I get a clean function that is robust to sampling noise. Okay. Now, it's interesting now, eigentasks give us, in a way, a set of functions, special functions yk. K is, there are 64 such functions. Each 64 function is represented by a set of these weights rk, which are obtained numerically or experimentally. And so these functions are those functions that I've plotted. They are special functions specific to your encoding. And another way of thinking about this is that instead of measuring in this basis, you're now effectively measuring in another basis with these coefficients that are obtained here. So this gives you, in a way, the eigentasks tell you about an optimal measurement basis that is matched to your encoding. Yeah, I'll pass this point quickly, but total capacity large doesn't mean that in a practical machine learning application that the machine learning measure, however you characterize it, is also high. And so here we are comparing a simple machine learning task on a one-dimensional view, and find that there's a correlation between doing that task well or not with the expressive capacity of the system, as the total capacity of the system. And there is, now in a physical system, you normally have, let's say in a physical system like this, you get exponentially many features. And so you don't want to deal with exponentially many features, and you would like to truncate those features in some way, right? Because ultimately, you want to simple calculation. So what eigentasks give you, what we learned, is that it gives you a way to truncate your basis, because it orders special functions with a certain sort of signal-to-noise ratio, and I can use these basis functions, yk, now as my new features, yeah? And I can say, then I can do truncation in that space. And there's a well-defined now truncation scheme that is given by number of shots that you do the experiment in, which is S, right? And we know that beta k squared with respect to S sort of makes a delineation. And indeed, I'm plotting here the classification accuracy in a certain machine learning task, which is a toy task, as a function of number of features used, eigentask features used. And you see there are many sort of curves here, but I want you to pay attention. The upper one is for correlated encoding, and the lower one is for product state encoding. And these lines here show you training accuracy. And you see as you increase the number of features, the training accuracy peaks. It's almost 1. Yeah. But if you look at the testing set of machine learning on unseen examples and you plot the testing as a function of this number of features, you will find that it's actually non-monotonic and there's a peak that is reached here and then it goes down. Yeah? And so that it means that you're starting to overfit here. Yeah? And so this point turns out to be the number of features that are equal to some value cutoff, and that is proportional to S we find for this simple thing. So number of shots gives you in a way a truncation scheme here. And this is true for sort of product state encoding and correlated encoding, except that for correlated encoding, it's much higher, this truncation point. Okay, now I want to show you that this idea of eigentasks is general and works also for classical optical systems. And there, where this is work we're doing with Peter McMahon from Cornell University, they are very interested in low light sensing and using physical neural networks to sense in low light. And one example is here. You know, they have actually built a 3D scene like this, and there's a 50 here, right? And so you want a optical transformer, certain, you know, some optical programmable thing, layers here, that take the scene, input from the scene, transform it, and then focus it here, and there you have an EMCCD camera which has only 4 pixels. And that should be enough if you want to maybe do binary classification. You want to see, is it 50 or is it not 50? Yeah, okay. And so what they do is they take these 4 features and they feed that input, digitize it, and then feed it through a neural network running on a computer. Now, this new project was sort of inspired by this idea, and the way to think about this is that the eigentasks, there are eigentasks here in an EMCCD camera, because this is like a set of, 512 pixels or something, which real valued sort of integrated quantities. And you want to send some input U, which is an apple maybe, and it goes through a scattering medium, and then you make one shot with a certain integration time, another shot. So an S shot result, will be, result will be averaged, and so this is your stochastic feature. It's as many dimensions as the number of pixels. And now we want to use feature reduction through eigentasks, and we would like to compare it through standard things for feature reduction in optics, in sort of vision pipelines, coarse graining, PCA, and so on, and eigentasks. So what we would like to do is find these many eigentasks, calculate them from experiments, and then get rid of some of them and use the high signal-to-noise ratio eigentasks. I think I should skip this. And what we find is that for this MPEG data set, 20 images per class, up to 70 classes. I'm plotting here accuracy as a function of number of classes. And you see the performance of eigentasks in accuracy on test set. And there's a statistically significant gap with respect to this low-pass filtering, for instance, in this case, and PCA and so on. Yeah, this gap narrows when you use larger number of shots, less noisy features. Yeah. So I want to finish the issue, complete this part about eigentasks and computational capacity, and tell you that the real, in our opinion, the real practical power of physical neural networks really lies in quantum measurement. Measuring complex quantum systems like this, And I want to sort of illustrate how this works, because we don't want to just have a physical system that generates a very low power signal, and that signal then couples to a physical system. And then we measure that signal and then guess the physical system state, right? This neural sensing approach, for lack of a better term, it's explained in this paper here why we call it neural sensing, is we think of the signal producing quantum system that we want to make measurements on. We couple this coherently with a quantum processor that will produce a robust measured signal that tells me about maybe quantum state discrimination. Yeah. So I want to prepare this physical system, maybe 3 qubits, either in this state or in this state. I want to make measurements on my, that excites this set of oscillators. I make measurements on these oscillators, and we would like that when we do, find the right weights on the input-output, in the output quadratures of the light coming from here, if I find the right weights, I want to be able to separate these two states, which otherwise would not be separable. And there is a basic case that sort of has been discussed in this paper. If you're interested, please have a look at this result, where it's shown that if these two oscillators, our quantum system I want to make measurements on, are in 2 quantum states, and I want to discriminate whether it's this state or that state, and if I just measured these oscillators, I would find that the mean of the signals that are coming out here will be the same for the 2 states, but the difference is in the covariances. Okay? And if you use standard techniques, because the mean is identical, it fails, we show, unless you do a nonlinear transformation up in the room temperature and do a lot of averaging. And here we show, by designing the system and the coupling and the nonlinearity of it, we can actually separate those 2 states. And the state is actually living in a 4-dimensional space of input-output quadratures of this, right? But there's this projected space where these 2 signals separate in an optimal way, and that requires that that separation is actually related to the coupling strength G12, and it turns out that this G12 gives more entanglement here, which is helpful in classification accuracy. This is, again, an anecdotal observation, but it's probably telling of something more interesting and requiring an analytical theory. So this brings me to the end of my talk. I want to just acknowledge the people behind this work, and the work that I've not talked about. They are all within the same pot. Said Khan, who now moved to Peter McMahon's group. Gary, again, a former PhD student who did this work and other works, who has moved to BBN. Fengjin, he is still with us. And Marty is a new addition, our collaborators at BBN. Essen from Princeton Computer Science, and Nick Brown from IBM Quantum. And the bigger collaboration that is behind this, Muri superconducting reservoirs for quantum memory and information processing, of teams from Cornell, Peter McMahon, Ohio State, Daniel Gauthier, Michael now at Yale, Shyam Shankar at University of Texas at Austin. Thank you. This is cool. Okay. Yes.
Thank you for the nice talk. I have a question. The slide that you showed us. And maybe I'm not very into this topic, so maybe it's a stupid question.
Yeah, absolutely. Yeah.
In these systems, you are increasing the nonlinearity, and you see that there is a higher degree of entanglement in
No. Yes, so I didn't have a chance to get into detail there. But what you can show is that if these oscillators are individually linear, okay, then there's no way to separate these two states. It's absolutely on top of each other. If you add nonlinearity, you start separating them, yeah? And maybe this figure is better. You start separating them. But if on top of this, you also increase entanglement, you optimize the separation in a way that with a very high Fisher discriminant. Yeah, that's the key. So, and many of you who knows about superconducting quantum systems will recognize that this is really replacing a quantum limited amplifier here. So it's like you can think of this as a, programmable quantum limited amplifier that does this. But the only difference from quantum limited amplifiers is that you operate them in a regime that you would normally not operate those quantum limited amplifiers, the nonlinear regime.
Thank you.
Okay, who else? Christoph.
All right. Yeah, thanks a lot. When you look at quantum imaging and sensing and so on in many systems, of course, people looked into that entanglement really helps, right? Because of the correlations that then, if you do it in a clever way, the combination helps. Otherwise, it can be worse, right? If you don't do it in the right way.
Right.
But what people also realized that actually sometimes it's also good to actually use classical correlations and to handcraft your classical correlations, for example, in the quantum imaging and so on. The signal-to-noise ratio will not be as good as with entanglement, but it still will be better than without the correlations. So could there also be something where you benefit just from classical handcrafted correlations?
Yeah. I mean, I'm very skeptical about this, immense purported power of entanglement. And here we start in a different place. We think of quantum systems not like this, incredible quantum physical systems that, have entangled features that will solve many of our problems. We are thinking of physical systems as the quantum systems as the absolute physical limit of how low power you can operate a physical system for computing. And in that sense, any correlation in the light field, let's say in optical systems, not here, but in optical systems, any spatial correlations or spectral correlations in the light field will contribute. And we can measure it by just looking at the total capacity with and without those correlations. And we'll hopefully, if you set up things right, you can characterize the role of those classical correlations in giving you computational capacity. Yes.
Okay, more questions? Maybe I have a quick question. So there's all these quantum advantage experiments where you just produce states with very complicated statistics. It seems at first sight intuitively that because they are designed to give you so complex statistics, they should also have very large capacity. Is that a correct intuition?
We didn't find a simple way of understanding the role of entanglement through an analytical theory. All we have is some anecdotal evidence from numerical simulations where we show, because now that we have this metric, we can talk about something and compare. And in the previous graph we have discussed, when we do the encoding with correlations and without correlations, we see a clear difference, statistically significant difference between total capacity. But I would say that advantage we see is only in the finite shot limit. Yeah. So in infinite shot limit, it doesn't look like to me that some entangled, system gives you a major advantage from the point of view of approximating functions. Maybe in other problems, other way of formulating it, it would. But for function approximation, we don't see clear-cut advantage. So it's only in the finite shot limit. And the reason we sort of understand but can't point it directly with our finger, and we would like to do that, is because when you have entanglement in your outcoming features, then the noise of features are correlated with each other in entangled systems in a more complex way statistically. So then there's more chance to, by adding them coherently, to cancel that noise if they are correlated. And if they are not, there's less chance to do that.
Okay, very good. Is there any other? Yeah, so there are two questions side by side. So watch out.
I really like this concept of eigentasks, and so I was wondering, how can I now apply this in practice to a classical optical neural network, for example? How can I extract them?
Yeah, well, experimentally or numerically, and we always make sure that our numerical results conform to experimental results. And so what you do is, let's say you have some input distributions, right? I mean, many cats and many dogs in the spatial light modulator. You look at the EMCCD recording for S shots and get the output vector. And then what you do is you say, I'm not going to do classification. I'm just going to show it, all these guys, without saying the label. Mm-hmm. And that input distribution, I build the matrix, this G and V matrix. I solve an eigenvalue problem, and we obtain the eigentasks.
So the reason why I was asking was, then it somehow depends on the input space. And
very much, yes. Very good observation.
I was wondering if you can, because if you don't make any assumptions on the input space, then you have a huge space to sample from.
Yes.
And this seems very difficult.
Yes. And this makes physically very sense. In a way, when I look at an image, I don't see all possible pixel combinations. Physical world gives us only a finite number of things. A cat, right, moves in an intact way in time domain, let's say. Yeah, you don't have a cat in one picture, all intact, and then in the next picture completely separating in pieces. So there is physics comes in here, and physics says that in the broad spatio-temporal domain, there is an identity to physical objects, and so they are determined by physics, physical laws, the laws of nature. And so, therefore, not all pixel combinations are those that I should be building functions on, but there are very few, things. And the input distribution tempers that, gives you regularization there. And so things become more meaningful.
Okay, thanks.
Yeah, thanks. Very interesting. So I have a question about now the measurement that you are doing on a quantum computer. So you calculate the expectation values of the individual operators on the qubits, where you lose actually information about correlations, right? Between
No. I measure actually the probability of a certain bit string measurement.
Right.
0, 0, 0, 0. I repeat the measurements. I get 0, 0. Next, I get 0, 1, 1. And then I make this, 1,000 shots, and I draw a histogram. So it's not individual qubits.
So you process the whole...
Yeah.
Okay.
Yeah.
Thanks.
Throw me. I like this idea. Yes.
Very good. So I think with that, we end the talk, and as usually, there's food outside. But before we go to take in the food, let's thank Hakan again for the experience.